I'll be giving the sort of next part of the holomorphic curve side of things and detecting knots with enhanced knot contact homology.
Great, thank you, Laura. So I guess I've put a general outline here. So I have a lot to say, but I've starred sections 0 and 5. In some sense, these are going to be the most important sections, maybe also the most, well, I don't know. There'll be a range of hand waviness, I think, throughout the whole talk, just to see how much I can get through, but hopefully I'll try to keep it somewhat clear. And one thing that I actually want to do is I want to start with section -1. Which I haven't prepared at all. But I want to say something just about, there's this paper of Chiliabak and Latchev, which essentially, you might be wondering why we were talking about broken strings and why we're sort of getting close to string topology in the first place. And essentially the picture that they have there is something like this. So if I take, suppose that I just have some Q, and I take the cotangent bundle, so say that I have T star Q is here. Let me just draw it as a box. One thing that I could try to do is I could try to study the contact homology of the outside. So we haven't talked about contact homology, but what is it generated by? It's going to be generated by certain Rabe orbits. And so one thing that you might want to try to do is to try to count things that sort of go from Rabe orbits up here, and where will they go? Well, you might think, there's not really, they can try to go inside of T star Q, but where should they end? And the point is, where they will end is they'll form some sort of loops inside of here. And in order to understand some holomorphic curves that sort of land in here, the things that you get, so you get these chain maps, but to what? Well, the things that you have in here are these loops. And they might have certain points where they kind of come in and start to intersect at a point. And so in some sense, you have to start understanding string topology on this side. And so you should get a chain map from contact homology down to string topology on this side. So that's sort of the version where you have that everything is closed. And what is the open version? So now if I take, sorry, everybody got that breakfast is 8 to 10:30.
That was the easy part of the talk.
What?
That was the easy part of the talk.
Yeah, that's right. So now instead, if I take the same picture, I want to study some sort of closed string version. So what I can do is try to study a Legendrian here. Let me just be simple and take as my Legendrian, maybe I'll put my Legendrian in blue as, I'll write just some conormal like this. And so if I want to study, what do I have up here? I have just the Legendrian contact homology, so that's kind of studying Rabe chords, where this thing is really, is going from the blue to the blue. So I have these Rabe chords, and what I might want to do now is to understand what holomorphic curves look like from down here. And so what would you do? You would want its boundary to stay on a filling of it. Say we take the filling LK. And then as this curve comes down, so now its boundary is going to start tracing out things like this, and I want it to be able to turn at Q. So you see, so I start having things that kind of turn at Q, maybe it comes down, maybe it turns at Q, and anyways, it comes back up to the other point that's there. So you see that up here, you have Legendrian contact homology, and inside of here, you have these sorts of broken strings that we were drawing before. So that's why we're studying these broken strings, is because this fits into this Chiliabak-Latchev figure. So that's kind of the first round of overview. So now that brings me to, any questions about this? Okay. So now that brings me to section 0. So the real overview of what I'm going to talk about. Okay. So what happens in, there's these two papers, which I'll just refer to as CELN and ENS. And in CELN, essentially what they do is they construct exactly this chain map, LCC star, so Legendrian on the chain level, from the Legendrian contact DGA for this conormal lift to this string chain complex with K. Okay? And this, they show, so this is in CELN, this induces an isomorphism on the level of H0. Okay? And one other thing that they talk about in that paper is that if I look at H0 on the string side, this is actually going to be some R, which is going to be some subring of the group ring of the knot group. So pi1 R3 minus K. Okay. So what I'm going to talk about, at least for the first 4 sections, is an enhanced version. So an enhanced version, this is again S. So what I can do now is I can try instead, I have that I get some subring of this, but I don't get this whole thing. One thing that you can do is try to add extra information. And in particular, what you do is you now look at the Legendrian contact DGA, not for just lambda k, but you also glue in a point. So P is just going to be a point in R3, which is disjoint from K. And what you're going to do is you're going to map this in to some other string homology, but now for K union P. Okay.
And what is lambda P?
So lambda P is just going to be the co-normal of the point P. So it's just, so it's just a 3-ball. And, it's a 2-sphere bounding the Lagrangian co-normal, which is a 3-ball. Okay. And I should say that there's also, you can look, when you study this this Legendrian contact DGA, there are going to be RAVE chords that start on K and end on K, start on P and end on K, start all these different versions. And so the ones that are going to be, the structure that's going to be relevant is that there's actually a 2 product. So I'm going to be lazy and just write R for LCC. And that's from RKP tensor RPK to RKK. So there's this Legendrian, I haven't told you what degrees these are in, but I'll tell you that in a little bit. And what this is going to map on this side to some sort of product structure. And the point is the product structure over here. So the last thing that Amelia started talking about was that you can show that, so she was saying something like this chord algebra, which was, so you had H0 string was some sort of chord algebra. And she said that there's some sort of homotopy formulation, which is really how you get this. You go through the chord algebra in order to get this. And what you have is now with this enhanced product structure, what you end up getting is that you can recover.
Sorry,
Yes.
Can you repeat the meaning of this KP, PK, and KK?
Yeah. So this is So I can just say this is going to be the degree 0 Legendrian contact homology with RAVE chords starting on K and ending on P.
Okay.
Yep. This is going to be LCH 1 to PK, and this is going to map to LCH 0 KK.
By the way, I've been told that we misgraded this, and so everything should really be in degree 0. We should have shifted things down, and anyway. And then the wrapped fleur also would be in degree 0.
So I guess the notation that I'll be following is such that this actually happens.
Ah, okay.
I assume, I don't know, maybe I'll make a mistake then as well. But anyways, be wary of the indices. So the point is, so from this and the product structure, it turns out that you can recover you can recover that if I look at Z and I append this to the tensor product RPK tensor RKP. So what I do is I have that this mu on the left-hand side ends up giving me a product on here. And I basically include a Z such that 1 acts by the unit on this thing. That gives me a ring, and as a ring, this is going to be isomorphic to Z. I'll just write Z pi k, where pi k is this.
So can I ask you,
Even if you recover Z, I mean,
So-
basically fundamental group of the node complement doesn't remember if you start with a mirror or if it's a original node.
So yeah, so I put detects in quotation marks,
Okay.
and there's a reason for that, which Roman has pointed out. Right. So let me just state this. So maybe theorem or corollary, if you like, of this discussion. Theorem is that, so if I think about this structure, let me just call this structure, I don't know, math frac G. So if I have this structure, then it determines the isotopy type of K up to mirroring and orientation. Furthermore, if I have an isomorphism, so if I have an isomorphism of the structure, so I get pi k, I can recover pi k, it turns out, from this, and if that isomorphism preserves the so-called peripheral subgroup, then I have that they're actually isomorphic. But let me just sort of say how this is proved. So the proof is that there's some sort of three-manifold theory fact, which is that pi k is left orderable. So this means that you can give an ordering on the elements of pi k such that if you multiply on the left by any element g, it preserves that ordering. And this implies then that z pi k determines pi k. So if I look at the units in z pi k, then plus or minus of the units basically are plus or minus of the elements here. And so that's due to, this is something going back to Graham-Hickman from 1940. And then there's a result of Waldhausen, which basically says this is enough. So. Waldhausen 1968 implies
I think you need that K is irreducible.
Yeah, this is not quite true.
oh,
I mean, Waldhausen's result says that this, along with the peripheral subgroup, determines not.
yes, okay, yeah, so I should say plus some algebra. So, yeah, so, okay, so one thing that you have to do is you actually have to look, you have to look a little bit at the algebraic structure, but I don't really want to talk about that for this talk, so, anyways, just a little bit of playing around with left orderable groups is enough.
I think the comment was that K has to be a prime knot,
Oh, yeah.
or else you have a granny and a square knot.
Okay. Maybe I'll put K as a prime knot. Just to. Okay. So section 1 is going to be about this enhanced string thing. So I'll be a little bit less careful about this CM business that Amelia was being, and I'll just sort of draw a diagrammatic picture of what's going on. So I have my Q is here. I have, here's LK, and this intersects with K. And I'll also call, so Q is going to be R3 forever in this talk, and if I ever write N, it means LK. And there's some point P here with some LP here. What I want to consider for broken strings now so what are these going to be? I'm going to write sigma sub L, but be careful, this L is going to be a different L than what was in Amelia's talk. So this is going to be the number of P switches. And essentially what I want to count is the following. So I want to count curves which either start, so I'm going to pick sort of a point and maybe a tangent vector on each of LP and LK. And what I want to count is strings that start and end on 1. They can go between them. That's totally fine. And they're going to have this sort of kerning condition that Amelia was talking about before. So just things like that. Okay. So I should say have switches with conditions matching holomorphic corners. So maybe let me be a little bit more precise about what I mean by this, by matching holomorphic corners. What I mean is that you can find, so I assume that I perturb K so that it's real analytic. So for P, this is kind of fine. The metric just gives me a way to associate this, and I take my J standard on the cotangent bundle. Okay. Now in holomorphic coordinates around K, what I can do is I can take, so around K, I have some coordinates so I have some 3 coordinates. Such that K looks like R cross 0. I have Q is going to be equal to, what is it going to be? R3. And LK is going to look like R cross IR2. And so the point is, if I have a holomorphic curve, so say I take some sort of curve from d epsilon plus, such that it kind of does a switch, or maybe doesn't do a switch, something like this, then what those coordinates will be, I can write, so let me call this u of z, I can write as equal to u1 of z in C. So this is in C, cross u2, maybe, comma, u2 of z in C2. And sort of the U1 condition doesn't really, I won't talk about the U1 condition, but the point is that the U2 that I have has to be a corner, so it needs to do something which maybe goes like that, or it can wind sort of, you're allowed to just sort of pass through, or it can sort of split like that. So the point is, the conditions that you end up writing, all these conditions that Amelia ended up writing were basically that U2 of z, maybe I'll just write this one. I'll write it down. Where that U2 of z ends up looking like a sum of ck z to the k, where k is in half of the natural numbers, such that, so ck supported either on n or half plus n. So either the k's such that ck are non-zero are either all integers or they're all half integers, and they're all either real or imaginary. So anyways, if you translate these conditions that Amelia wrote down, at least on the first derivative, into this sort of thing, then you get this analysis. So anyways, once I have this U2, what I can look at is the first ck, such that this term is non-zero. And that allows me to give a winding number. In some sense, it's whether my curve went like that, it's whether my curve went like that, it's whether my curve went like that. So I see that I've already gotten ahead of myself maybe, but this is why I should follow my notes. Okay, so I can set W of whatever, the switch point is a local winding number is equal to the min k such that ck is non-zero. Okay. So this is, it could be in a half, 1, etc. Now I haven't actually, So I've defined the broken strings that I wanted to consider, but I haven't actually told you about the differential, so there's some extra terms. So I have that, I still have this differential. I'm really considering d simplices of these things, generic d simplices. And remember, L was the number of switches at P, not at K this time. So del goes to CD minus 1 of sigma L. I have that, I have del N and del K corresponding to, del Q corresponding to this K, which are going to go from also CD sigma L to CD minus 1 of sigma L. So the number of K switches will change, but not the number of P switches. But analogously, I can also define CP of LP and del Q of, del P of Q. And since I'm just seeing the number of switches that hit a point, that only happens at a codimension 2 subset. So now that degree, so CD of sigma L, is going to go to CD minus 2. But what do I do? So how are these things defined? Where I inserted an extra spike. So you see that the number of L switches goes up by 2. And the claim now is that, so claim, which I won't prove, is that the total differential, maybe I'll just write it as del sub k and del sub p, where I just have the sum of all those things. If I square it, this is equal to 0. And I want this to be a degree minus 1 map. So what do? I essentially just take the degree m, so Cm is going to be the direct sum such that, let me see if I get this right, d plus L over 2 is equal to m. Anyways, if that's not right, it's not a big deal. I better. Next one. Now, the problem is that some of these things are actually, I have that some of these things sort of, I can now break them up into ij. Maybe I'll just write all of them. I have CMKK, CMPK, CMKP, and CMPP, where remember I said that I could start at either of those 2 points that were up here. So I can start and end accordingly. And the problem is that these actually have half integer degrees. So what I can do is I can just add a half to one, I don't remember which one, and subtract a half from the other. And that gives me, so if I take this complex together with that differential, that gives me the correct string differential that I want. Any questions so far? Okay. I should also say that there's a Pontryagin product. So what is this going to be? Let me just write, so Pontryagin product. So this is a map P from, maybe P isn't the, maybe K isn't the best choice. Okay, CM1, KP, sigma L1, tensor CM2, PK of sigma L2 to CKK of K1 of, M1 plus M2 and sigma L1 plus L2 minus 2. So you can check that with those indices, this is going to be degree 0. And what is the product? So, is this already dying? Yep. Black markers don't like me.
Everybody else likes black markers.
I'm a fan. I'm still using it, right? Okay. So what is this product? Let me just look at LP and sort of forget about the LK that's over here. Suppose that I have a string that's coming in, and so I might have So I have some sort of string that ends at this point that I denoted. So that's coming in there. And I have another string which is leaving this point. I mean, of course, it's staying on this actual thing and making a switch, but easier to draw. So what do I do in order to concatenate these? Is I just turn this into basically the thing where I take this spike that was coming off, and I just bring it all the way down here. So now it has 2 less switches. Okay, so that's the Punchy-Eigen product. And I should say just this descends to homology. So descends to homology. You can check. Okay. Great, so that was, of course, longer than I expected it to be, as every talk is. But are there any questions at this point? Okay, so now I want to relate, so this is section 2. I want to relate C twiddle string to this, to the group ring. So how do you do this? Well, essentially we saw that we had this chord algebra, and the point that I want to make is that you can sort of turn the chord algebra into an enhanced version where your chords will start and can also start and end on either K or P. And so this allows us to come up with sort of, we have chord KK, which was just an algebra in itself. That's the thing that we originally defined. We have chord KP, and so on. But let me just say, chord KP, this guy is going to be a left KK module. And the point is, when you see a Skine relation which looks something like the following, so let me put K prime above K as in Amelia's picture. So we're going to take a difference there. Okay. So if I take a chord now which is coming under and one which is coming over, I had that this was equal to sort of being multiplied like this. This is something we've seen. Well, suppose that I have now that this is KP. So this ends in P somewhere. Well, then this thing will be in KK. So this is giving me the left action of chord KK on KP. And I see that this now starts on K and ends on P. So these things start on K and end on P. So I can just interpret the Skine relations, in particular 2, 3, and 4, not 1, as giving you a module structure. So anyways, I can enhance this thing. And the point is that this is essentially, this mirrors in the same way that Amelia was describing at the end of the last talk, the string homology. So this ends up, if I look at, right, so I also get a map chord PK, tensor chord KP, to concatenating, so you just concatenate chord KK. Of course, you have to be a little bit careful. Like there's a base point that's sort of here. When you concatenate, if you want to match the ends, you have to match them such that you didn't go through the base point. This concatenation is a proposition that this is going to be isomorphic to the pair of pans product on H0, KP, string, I don't know where to put all the decorations, tensor, H1, PK, string, with the Punchy-Eigen product to H0, KK, string, obviously. And maybe with the tildes, just to...
I'm concerned about what chord PP means. Like,
Sorry?
what is there also a chord PP?
Yes, but
Does it have like one relation?
so it's really what you should define if you wanted to define it is you should think about chord PP as being equal to how do you define it? Maybe.
If it's not.
Oh! It's going to be something like chord PK tensored, but now over chord KK. With chord KP, something like that. I think that's right. Okay. Anyways, since I'm running low on time, I'll just say that you can now write this. This is very close to sort of these homotopy groups, and that these chords are sort of going around the. They're sort of. I mean, you can think about them as sort of winding around the ambient space Q. And maybe like near here you have some sort of ambiguity with how many times you looped around the meridian or the longitude, but you can encode those purely in a combinatorial way. And so that allows you to come up with some sort of module of words. So this is going to be very hand-wavy, but you can come up with some sort of module of words alternating between maybe it's best to write it the same way. And the point is you sort of have product structures on this also. You can check that all of these maps preserve the product structures and everything like that. And so if you just work on this level, this gives you an isomorphism of so you end up getting that this Z plus chord PP, you can give this a ring structure, and this is going to be isomorphic to Z pi k. So sort of on that end, you're done. Sorry if that's fast, but I do want to get to other things. Okay, any questions so far? I think I'm going to end up skipping section 4, but I want to say something about this actual isomorphism. And I promised Roger yesterday that I would define Legendrian contact homology in some way. Yeah.
So from the on the right side of the board, you have the tensor to the chord KK is a product, and then for PP to the tensor is a coproduct. Like why it's not symmetric? Like why one is product and the other is coproduct? There's no coproduct. That's the definition of a chord PP.
Yeah. This is just equals. No math. Just equals. I'm just setting it equals. Great. Thank you. So okay. So one thing that you can do when you define Legendrian contact homology is, well, I guess Yin sort of talked about this a little bit yesterday. But you can kind of do things where your generators, so let me just talk about LCC star instead. The generators instead are going to be something like this. So I pick some x naught, which is going to be fixed in whatever my Legendrian is, and I now consider things that look like this. So these guys on the bottom, C1, C2, C3, are going to be rate chords. And these paths, alpha 1, etc., alpha 4 maybe, these are just going to be paths in lambda. And sort of the point is, instead of just modding out by homotopy to start, you can actually just you can just basically say, consider these things, and you can consider, D chains of such things. So that's, you can basically do that instead. And one thing that you get from this is that you can now define Legendrian contact homology in a slightly more refined way, which is to say that, in the first place, you can take, so I now have CD of, say, RL, where L is like the number of RAID chords that I have. And I can just take a differential to CD minus 1 of RL. So this is just a regular differential, singular differential. And I can also take sort of the symplectization differential, CD, and let me write index instead, so this is not the number of RAID chords. This is going to map to CD of R index minus 1. And essentially what this differential counts is, so I have one of these guys. I want to take a differential of it. What I do is I sum over each of the CIs with the usual differential. So I take such that this moduli space mod R is 0-dimensional. Sorry, I know I'm being very fast. So I basically sum over this for each of them. So that still gives me a D simplex because I have that this is D-dimensional up here, but each of these is a 0-dimensional modulus once I modify R. So anyways, what this allows me to do is to say, well, okay, D sing plus D symplectization squared is equal to 0, and and the total degree I can take to be D plus the sum of the indices of the RAID chords. Is this fine for you?
Is it really a sum, and is it really D and 0? It's actually D minus K and K, right, for all Ks. Yeah, and it's okay.
Okay. All right. Anyways, yeah. So, so in fact, if I take this now, then I get an invariant, which is really the Legendrian contact homology. And if I filter by what do I want to do? By the index, is that right? Then the E1 page of the spectral sequence, in our case, gives the usual LCH. I mean, sort of. So you can see that this is kind of the same thing.
I think I'm getting confused by the D and index.
So the degree is like the D is, you have some chain of these things.
Mm-hmm.
And then there's also the RAID index just on there. Right.
Okay, and so your spectral sequence is like vibrated by those two things, and then
Yeah, exactly. And so on the E1 page, what you're going to get is something like, H0 of R del sig. So you sort of mod out by the homotopy classes already, and you're going to have that the differential on the E1 page is just going to be the symplectic differential. Okay. So, so now what is the chain map going to be? Phi from LCC star. Oh, and of course, the Legendrian contact homology, I can have, if I have a RAID chord here, I have that, if I have both my P and my K, I can have the sides can be in P or they can be in K. They can sort of go between them also. So you can keep track of that information and come up with an LCC star KB and PK, etc. So anyways, if I look at this differential LCC star to C star string, twiddle, then what I'm going to get is that this is just going to be a count of things which are, so I have a RAID chord, say, on lambda p cut lambda k. And essentially what I want to think is that what this is doing now is when I take this differential, I have that if I read this word along, that's going to be a broken string. So this is the picture that I sort of drew before. But you have to be a little bit careful about this. And I'll say a little bit about it. A little bit. I mean, one of the things that you have is, you know, you can think about instead, now this version of LCC that I constructed, this is actually going to be, there's going to be like a D chain of such things on this side. So in some sense, what I get out is going to be also a D chain of such things on this bottom side. Like, but
What are your two sides?
sorry, the top side is just the Legendrian contact topology, which is just the ray parts here, and sort of the bottom side is everything starting at this corner, going down and sort of going around to this corner, so the broken string side. That's what I mean. So if I have like a D family of these, then I get a D family of broken strings, but I need to be a little bit careful about what happens on the boundary and check that it's commensurate with everything that I want. So so essentially, yeah, so I need to essentially study moduli spaces of such things. And there's a few ways that they can break. So the thing that I end up studying is the moduli spaces that I study are going to be things such that the winding numbers at each of these points, oh, there might also be P switches where there's no real winding number. So maybe I'll just draw that. For example, maybe that's a P switch there. All of these are going to be 1/2s. So you're just going to have sort of normal corners. And I need to now understand something about how these moduli spaces compactify. So there's a few ways that they can compactify, and maybe just for simplicity, I'll forget about the P quarters. The ways that they can compactify are as follows. I could have something like these 2 points could essentially come together and form now a big point with winding number 1. Like that. I can have this either on the N string or the Q string side. So this is called, so this sort of convergence is called lag. And I can also have sort of that something like this can converge to something where I get a symplectization end. So this is on the symplectization end, and then these are like the types of curves that I'm counting down here. Are these like moduli spaces of curves? So this is called SY. And essentially the point to make.
Did you mean to have more?
So right. So essentially the point to make is that something like this, where these 2 winding numbers come together, what I can think about as this being in the boundary here, it kind of looks like everything approaching this sort of had something nearly being a spike here. So when I approach this point, what I need to send this to is something which still has that spike on it. Okay. So in that sense, being a little bit subtle with that, I have that I can send my phi over here, and it ends up being a chain map. And I think I'll skip about 5 pages. Okay, great. Sorry, I know that was fast. Any questions? Okay.
Do you have any properties of this chain map?
Yeah, I mean, yeah, you need to check. Yes. You sort of, let me write out the relevant equation. Essentially what you need to check is that, what is it? Something like phi of A. So if I just have a rape chord, then this should equal to something like phi of del symplectization of A minus del phi of A, where this is like the sum of all the deltas. So the point is, when this appears on the boundary, and basically what I'm doing is I'm sending the moduli spaces over to some chain of broken strings. And so when I send the full moduli space over, it's kind of obvious what I do at a point like this. But as I approach one of these boundary points, it's not so obvious. And I just have to attach a string in order to make it set, and then that basically gives me this term. Okay, so let me talk about, let me do this without notes actually, maybe it'll be better. Section 5. So this was one of the starred sections, so if you're asleep, then wake up. There's some conjectural relation to this whole picture, for this whole picture with some sort of partial wrapping. So let me define this partial wrapping. What I can do is I can start with, here I have my T star R3, and I'm going to draw it a little bit differently. I'm going to draw it just like this. So, you know, you can imagine a zero section living somewhere in here. And what I do is I consider my Legendrian here. This is going to be lambda k. And so in the symplectization end of this manifold, so if I just attach the symplectization end to this manifold, then what I have is I have some sort of cylinder coming out like this, and that has a neighborhood to it. And what I can do is I can just attach that neighborhood and then smooth the corners in some sort of canonical way, so that I end up getting some new, Weinstein, some new sort of Liouville-looking thing with like a puncture. Okay. You can think about this as also, if you want to, you can think about it as a handle attachment along that Legendrian, where what you do is you send the critical point all the way out to infinity. So you just have that sort of, as you get to infinity, you see nothing but the co-core.
Or it's like deleting the co-core?
Yeah, it's like deleting the, yeah, exactly. It's like deleting the co-core, exactly. So,
Is it a different Weinstein map?
yes. I mean, it's not even a Weinstein. It doesn't have boundary at some point. Like its boundary is non-compact. Right.
You see, it's like Weinstein stops.
But it
Yeah,
contracts down.
No, but I mean, it's genuinely different. The Weinstein structure.
The structure is
Yeah,
different.
so I'm about to say.
It's like sort of, the completions are the same.
Well, it might be some, probably some conformity to Weinstein manifold, but we
No,
don't care about the
of course you
structure.
can inform it, or whatever
Yeah.
stuff you just like make it point out.
Then isn't the structure we care about here. If you think of it as some kind of.
No, but it's very much, it's different.
It sort
So-
of looks like it retracts down to the original Weinstein manifold, but where you've deleted lambda k
Mhm.
boundary.
Exactly. So what I can do is, you know, a neighborhood of this guy here is just going to look like a cotangent bundle. So what I can do is I can set like my Liouville vector field out here to be something like P del P. Okay. And so this is going to, you know, I have to interpolate in some standard way, but that's kind of fine. So I have just, you know, this guy. And what I can do then is I can take this and I can try to do so a full wrapped. So maybe I'll just call it wrapped. So a wrapped Floer homology. I can try to study wrapped Floer homology on this. Now, you know, you might ask what Legendrians do, what Lagrangians do I want to take to actually do the wrapped Floer homology, and what do I even mean by wrapping? Well, I mean, this sort of gives me a symplectization end that I can attach, and I just take standard standard things of the form AR plus B, as Sebastian told us this morning, and so you can do the wrapping in that way. So it's kind of like things out here kind of get wrapped a lot, but in here they kind of just go, they just sort of follow geodesic flow, I guess. Yeah.
So where does it get wrapped a lot?
So I mean, it's sort of difficult to draw it like in higher dimensions. Somehow the picture is bad in this dimension. But you know, in general, you'll have Rabe orbits here which don't get anywhere near this Legendrian, and so those Rabe trajectories that don't get near are going to get wrapped a lot. Okay.
But if it tried to wrap into that
Yeah.
thing, it would just kind of like never reach
Right.
the other side.
Right. Yes. So I mean, things can kind of, I mean, Rabe orbits can kind of come up here and down here. So this is the picture that Amiel was drawing before, where what you had was, you know, if this was my Legendrian, and I had my sort of surgery region, right, I might have Rabe orbits that kind of come into here, And then in this surgery region, if I just look at the core of the handle attachment, so that's the core of the handle attachment, then, right, sort of shifting in this direction kind of shifted which direction you shot out by a lot, but you could go any direction. The difference here is what we're doing is we're taking a puncture, we're sort of deleting the co-core. And so what happens is in this picture, you also have to kind of talk about how many times you wrap around the central point. So anyways, the point is if you understand the BEE picture that was being described before, then it turns out that you can turn, so you can try to study, so maybe let me just draw two Lagrangians that might be interesting to you. In particular, you can draw just the fiber, which was LP, and you can draw a co-core up here, which is just C, and try to do the wrapped floor homology of those Legendrians. And what you'll get, if you just sort of understand this BEE picture and look at all the relevant moduli spaces and whatnot, is that if I look at CW of CC, then this is going to be equal to some sort of A0KK. What this 0 means is just that there's no mixed chords in this part. So this is basically modding out by things with at least one mixed chord, in particular at least two mixed chords, because you have to go back and forth. Right. You get that CWCF is going to be isomorphic similarly to A1 of PK, and CW of FC is going to be isomorphic to did I mess this up, or is this where the notation the indices get?
So this is not where it
yeah.
moves it up.
Okay. So anyways, you get this together with your, and basically then CWFF is going to be Z together with something like A2 PP. And if I take homology now, then this homology is going to give me just that Z pi k from before. There's a lot that I haven't said about the product structure and what moduli spaces you actually have to analyze and how the chain map actually is a chain map. But anyways, I guess I'll stop there.
Really
Yeah.
good question. Just to make sure I'm thinking about this correctly, the straight black lines on this picture are contact manifold, and then synthetization somehow.
You attach the admins sort of out here. Exactly.
So you said this is conjectural, or?
It's
Progress, or?
depends. The level of conjectural I think depends, sort of varies, but I think everybody agrees conjectural, but some more conjectural than others. That's my sense.
So, like, when you do this wrapping in the punctured handle, like that winding number around the hole, how does that appear in? Yeah, so what you're going to get is what are the generators going to look like? They're essentially, just let me do the KK place. Then it's going to look like some sort of words of the form lambda to the A, mu to the B, because this thing that you're puncturing is really the full lambda K this time. So you have to keep track of that homology, together with some rave chord on lambda K, and then you keep on doing this kind of thing, C2, ... and then at the end, CK, and lambda B. So it's going to look something like that, where this is encoding how much you sort of wound around here, and this is the same sort of rave chords that you had done here.
So I have a semantic question for the not theorists. So when someone says this is a complete non-invariant, do you usually mean it can only distinguish prime knots?
No, this actually is a complete non-invariant. So the deal is the only fine print you need to say is that the conormal torus, you have to keep track of the class of the longitude and meridian. So the statement is that the Legendre and isotopy type of the conormal torus that are parameterized in the sense that you keep track of longitude and meridian is a complete non-invariant. So the point is that allows you to recover this peripheral subgroup. Full stop, no mirror ambiguity or anything. And that by this result of Balthausen is sufficient to detect the knot, whether it's present or not.
And where was that in this construction?
This is basically this lambda and mu, these homology coefficients on the conormal of J.
Yeah. Yeah, so this LCC that you've constructed has these Hobitovi classes of paths sort of built into it. That gives you these coefficients.
Is there like distinguished elements in the homology that, like that together with the homology detects the knot?
Yeah, but I would say it's on the context side. This is just the usual base coefficient ring in context homology. It's the one with the Legendre. So the usual SFT stuff says that this is invariant, or the usual invariance for LCH says that this is invariant, meaning that if you have two isotopic things, then the map preserves this base ring.
Any more questions? All right, so we're gonna have